The dark side of the universe. On the hunt for the ultimate cosmic monsters. While scientists scan the heavens, advanced computer simulations reveal the strange power of the black hole. Venture beyond the point of no return. To nature's ultimate no man's land. Welcome to our neighborhood. The Milky Way is just one of over 100 billion galaxies in the universe. And our sun, it's just one of over 100 billion stars in the Milky Way. We used to think of each star like our sun, as a friendly beacon amid the long night of space. Now, we know better. The universe wields violence beyond comprehension. Forces capable of tearing space and time to shreds. Join us now on a journey to the dark side, straight inside a black hole. Cape Canaveral, Florida. Our quest to understand black holes is about to enter a whole new dimension. Tucked into the nose of a rocket is a telescope called SWIFT. Its mission? To hunt for perhaps the most elusive objects in the cosmos. Black holes are so dense, not even light can escape their gravity. They defy detection. But today, hopes are riding high.
7, 6, 5, 4, 3, 2, 1. We have ignition, and we have
Scientists are counting on SWIFT to transport them to the frontiers of human knowledge and beyond. How do you find something that hides in the dark? You have to look for its telltale signs. SWIFT's instruments are designed to record bursts of high-energy radiation. Gamma rays don't penetrate Earth's atmosphere, but out here in space, SWIFT's view of them is front row center. They erupt when a black hole is born. That happens when a large star dies in a blaze of glory called a supernova. It's an explosion so powerful, it's as bright as a billion suns. What triggers that chain of events is the force that rules the cosmos: gravity. Scientists used to think of gravity as some kind of mysterious power, that objects like the sun project across space. But what if it's space itself that gives gravity its pull? That's the way one man saw it. To Albert Einstein, space is a bendable four-dimensional fabric he called space-time. And gravity? That's the warping of the fabric by massive bodies. They literally put a dent in space-time. Objects get caught in their groove and simply drop into orbit. Einstein's theory was a radical notion, all the more when taken to its extreme. Just how warped could space get? Scientists found the answer in a singular class of star, more than 25 times the mass of our Sun. It's earned its name, a red supergiant. This star will live only a few million years, a fraction of our own Sun's lifetime. Deep inside, the crush of gravity sends temperatures soaring above 1 billion degrees. Lighter elements fuse into heavier ones. Hydrogen becomes helium, becomes carbon, on up to iron. The core grows so heavy, it buckles in on itself. Then, the collapse sends a shock wave roaring out. The star digs itself deeper into space-time as a black hole forms at its center, and the giant goes supernova. When the dust settles, what's left is a black hole, an object 1 million times the mass of Earth, but 1 million times smaller. A black hole is literally a puncture in the fabric of space-time. Venture closer, and gravity becomes a riptide. It's like riding a raging river that's pulling you faster and faster toward a waterfall. The closer you get, the stronger the current. You're headed for a point of no return. In cosmic terms, it's called the event horizon. Over this edge, there's no escape, not even for a beam of light. Black holes are gravity to the max, and yet they are altogether commonplace. Astronomers have actually detected dozens of black holes in our galaxy. They estimate there are tens of millions more. But then gravity doesn't stop there. It turns out there's a whole other breed of black hole out there. Peering into galaxies beyond our Milky Way, astronomers have found that nearly every one harbors an immense black hole at its center. One galaxy steals the show. It's called M87, and it's got a black hole 4 billion times the mass of our Sun. It has left its signature, a powerful jet erupting out at nearly the speed of light. Where does a hole this ferocious come from? To find out, turn back the cosmic clock 14 billion years to the beginning of the universe. the Big Bang. Matter and energy rush outward as the universe expands. To learn where supermassive black holes came from, scientists have recreated these early times with supercomputer simulations. They can trace the long, steady process that formed galaxies. From the start, gravity reigns in the cosmos. It draws together the primordial gases. These aren't gentle clouds. As they grow more and more dense, they heat up. Over millions of years, they become hot enough to ignite. The first stars are born. They end their lives in powerful supernovas, while their cores collapse into black holes. Billions of years later, and across billions of light years, Swift is today scanning the heavens for these same early supernovas. It's helping us learn what became of those black holes that formed in their wake. Astronomers believe some grew huge by plowing their way to the centers of their host galaxies, where they gorged on a rich supply of gas and stars. Some black holes grew larger still when they crossed paths with others. This scientific simulation traces the collision of galaxies, a drama that plays out over 2 billion years' time. The two galaxies become one. The black holes in their centers merge into a single powerhouse of staggering size. The gas hurtling into it gets jammed, heats up, and erupts in ferocious waves. Blast waves from supermassive black holes can stretch for thousands of light years into space. They may lay the framework of the new galaxy, sculpting its size and shape and stocking it with something unexpected. Black holes may be one of the chief ways galaxies get seeded with elements generated by stars, with carbon, oxygen, and iron, the stuff of solar systems, and us. So, how did our galaxy make out in all this? Astronomer Andrea Ghez wants to know, have we got a supermassive black hole of our own? For more than a decade, she and her team have been coming to the heights of Hawaii's Mauna Kea volcano to find out. Working at the giant Keck telescope, Andrea is tracking a strange presence in the center of our galaxy. A group of stars is swirling around it, and she's clocking their speeds, projecting their orbits. Her telescope is so powerful it can peer through the thick of the Milky Way, through 26,000 light years of cosmic dust, all the way to the stars at the galactic center. Whatever's got them in its grip, it's accelerating the ones closest to speeds of up to 3 million miles per hour. Given that, Andrea and her team calculate that the culprit weighs in at almost 4 million times the mass of our sun. Solid evidence that at the exact center of our galaxy lurks a supermassive black hole. Andrea has confirmed the black hole is there without actually seeing it. So we're left to wonder, what's it like up close and personal? We can stop wondering and pay the monster of the Milky Way a visit. There's no spacecraft heading there anytime soon, but that's not stopping us. We'll get there courtesy of the latest telescope observations and computer models. We're just leaving the suburb where we live, about halfway out from the center of the galaxy. The Milky Way stretches before us. It's so large that it takes a beam of light 100,000 years to cross from one end to the other. Next stop, our galaxy's central hub, brimming with stars, known simply as the bulge. The farther we travel from our quiet cul-de-sac, the more crowded it gets. Up ahead, it's one big traffic jam of dust, stars, and hot gas, and it's always rush hour. Approaching dead center, the way is already strewn with signs of havoc, supernova remnants, and swirling clouds. Our course so far has been charted by astronomers like Andrea. They've plotted the landmarks by how they register across the light spectrum, from radio waves to X-rays. But here, their observations reveal a no man's land, an inner zone cleared by the voracious appetite looming ahead. A cloud of super-hot gas is swirling round it. The black hole pulls the gas in, then spews much of it back out. Now things get really strange. What you are seeing is not the stuff of Hollywood special effects. It represents the first time scientists have visualized the journey into a black hole. Their guide is Einstein, and what his equations tell them. Space here is so warped, the black hole acts like a giant lens, twisting the light that scatters across it. At last, we cross the event horizon, the point of no return. But don't expect the inside of the black hole to be dark. Swirling within is a maelstrom of energy and matter. Hidden in the chaos is a single point where the black hole's mass is packed, known as the singularity. Now imagine there's an eye to this storm, magically made calm, so all the strange predictions of Einstein's equations can play out. We'd be greeted by a passageway, an escape hatch in space and time known as a wormhole. Through it, we enter a white hole. Here, the same twisted logic holds in reverse. Instead of being drawn in, all light and matter are flung out. But to where? A wormhole is just the thing for a science fiction character in need of a quick getaway to another universe. Unless the truth be told, the inside of a black hole is too violent a place for a wormhole to actually form, let alone for the likes of us to venture. This is nature's ultimate fury. Destruction on a scale beyond comprehension. Or is it? In fact, it's simply the workings of a restless universe. A long time ago, when this black hole was young, powerful winds roaring from it seeded our galaxy with elements. They may have helped form a sun and planets, and some beings who could look into the sky and ask, what is a black hole? Our search for the answer is turning up dark mysteries and radiant revelations, secrets stolen from the other side of infinity. Welcome to Planet Earth. Journey into the workings of Earth's great life support system, the global climate. Learn what makes our world so conducive to life, and what ruined our sister planet, Venus. Explore the winds, the oceans, and the forces of nature that shape this dynamic Earth. Imagine the Earth is a machine, a system of cogs and motors, powered by the sun, batteries included. But our world didn't come with an owner's manual. How does it operate? What are the inner workings of this grand and elaborate system known as planet Earth? And why is it so conducive to life? Scientists have launched an armada of satellites to help us understand what makes our world tick. They're discovering the answers strewn across its atmosphere, on every ocean and continent, in the far reaches of the solar system and beyond. Like any machine, the Earth is the sum of its parts. They were forged in distant furnaces of our galaxy. Supernova explosions. When ancient stars erupted, they showered the Milky Way with heavy elements: iron, calcium, potassium, the very stuff our bodies are made of. But supernovas are also thought to bombard the galaxy with lethal high-energy particles. What safeguards our solar system is our star. The sun provides a shield stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere: hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick sulfurous clouds. Down at the surface, Venus's atmosphere is choked with high concentrations of carbon dioxide. CO2 is a potent greenhouse gas that traps the sun's heat. It has turned Venus into a cauldron. With surface temperatures of almost 500 degrees Celsius, this is the hottest planet in the solar system. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own, a powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night and the seasons. That causes warm tropical winds to blow toward the poles and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over. It breaks down in massive whirlpools that spread warm tropical waters over northern seas. Below the surface, they mix with cold, deep currents that swirl around the undersea ledges and mountains. Earth's climate engine has countless moving parts, tides and terrain, crosswinds and currents, all working to equalize temperatures around the globe. But when tropical heat builds to extremes, it can be released in a fury. In August 2005, within a huge looping section of the Gulf Stream, Hurricane Katrina. This is a supercomputer model of Katrina, a tool for scientists to better understand the dynamics of the hurricane system. To visualize the flow of air into the storm, they release a series of virtual streamers. Those with lighter colors are warmer winds. As they rise, they collide with cooler air above and produce clouds. The winds increase the evaporation of warm seawater, which draws more and more heat from the ocean and causes the winds to accelerate. Moving around the eye of the storm, winds can reach speeds of up to 250 kilometers per hour. A powerful hurricane like Katrina can release as much heat energy every 20 minutes as a 10 megaton nuclear bomb. While storms release heat stored in the ocean, the moisture they stir into the atmosphere helps keep the rest of the planet warm. Water vapor traps solar energy, along with carbon dioxide, the same greenhouse gas that ruined Venus. The difference is that Earth has found a way to keep CO2 in check. We can see it for ourselves by flying down to the ocean. The special ingredient that sets Earth apart is called life. The oceans are chock full of it. Too small for our eyes to see, phytoplankton may be the most important living things on the planet. They take in CO2, driven into the oceans by waves or drawn up from the deep by currents. They release the oxygen while absorbing carbon. The carbon then begins a journey up the food chain. Phytoplankton get eaten by zooplankton. To name a few, radiolarians date back to a time over 500 million years ago, when life exploded across Earth's oceans. Copepods are tiny bug-like crustaceans. With over 20,000 species, they are the single largest source of protein in the sea. Moving up in scale is a host of creatures smaller than the tip of your finger, including these octopus larvae. They get eaten by small fish. And they, in turn, by larger ones, like jacks. They are consumed by the largest predators in the sea: orcas, tuna, sharks. At each step in the food chain, the carbon that began as part of a diffuse gas in the air is passed on to larger and larger animals. The larger the body, the greater the mass of carbon. One creature goes all out. A humpback whale eats up to 1.5 tons of food per day. That's a lot of carbon. From whales down to tiny phytoplankton, marine life is part of a global system of removing CO2 from the atmosphere, then gradually releasing it back. The key to this carbon cycle is Earth's ability to store it long-term. A NASA satellite tuned to read chlorophyll, a chemical tracer for plant growth, shows the global biosphere in action. In sync with the seasons, plants take in vast amounts of carbon dioxide and release the oxygen we breathe. On land, the carbon can then find its way into the ground when plants and animals die and decay. The Earth, too, gets into the act. Exposed rocks take in CO2 when it rains. Erosion sends it into the oceans. If it becomes part of the marine food chain, carbon-rich matter can sink all the way to the sea bottom in the form of waste. Countless organisms like the salp, a jellyfish-like creature the size of your thumb, live and die each year. All the waste, all those bodies with their stores of carbon rain down onto the ocean floor. They pile up, layer upon layer. In time, these carbon-rich sediments can turn to oil or to rock like limestone. The carbon can return to the environment as CO2 if the rocks become exposed, or if they get pushed deep underground by the movement of Earth's crust in a process known as plate tectonics. The pressure and heat gradually build until the Earth begins to erupt. Every year, over 100 million tons of carbon dioxide is spewed into the oceans and atmosphere by volcanoes. Acting on timescales of a day to millions of years, the carbon cycle has helped make our planet habitable. But its success depends on life itself. We are how Earth works. If somehow the carbon cycle went wrong, what would Earth be like? The answer is a world away, on Venus. Here, the CO2 belching from volcanoes isn't going anywhere. Venus is like a house on fire, with the windows forever closed. The cause can be traced in part to those incinerating solar winds. Sheltered from those winds, Earth has kept CO2 levels in balance by absorbing and releasing it in roughly equal amounts. Lately, that balance has been shifting. The amount of carbon dioxide from human activities, including cars, power plants, and factories, now exceeds volcanoes by over 200 times. Much of that is from the burning of oil and coal stored in the Earth for millions of years. Since the Industrial Revolution, the amount of CO2 in the atmosphere has increased nearly 40%, with most of that in the last 50 years. The result? Global temperatures have risen by almost 1 degree Celsius. That's enough to accelerate the melting of vast stores of ice on high mountains and in the polar regions. Since the 1980s, NASA scientists have methodically tracked the Arctic's seasonal changes. They've found it's lost a quarter of the area covered by ice in summer. What's left has also thinned dramatically. That's just the beginning of changes that could transform our world, with some regions getting more rainfall, others drought. Deserts expanding, natural fires becoming more prevalent, wildlife habitat shrinking, polar regions becoming forested. And as the ice melts, it drains into the oceans. By the end of the century, sea levels are now expected to rise as much as 1 meter, inundating coastlines around the world. As our impact on the climate has grown, we've also gained a new perspective on Earth. From space. Technology is allowing us to take stock of the elaborate interconnected climate systems that protect our world and sustain it. within the fold of wind and water, of time and tectonics. Our planet has nurtured another extraordinary participant, life. Today, we are masters of a world revealing itself as more and more wondrous than we ever imagined. Even as we continue to explore its workings, we ask, is our goal to spend Earth or save it?